Hello guys and welcome back to Unbothered. Today we're going to start a new series with our Discrete Mathematics series. So this is the first video in the series and it is an introduction to sets. So I'm going to be adding a lot to the series. Obviously it's called Discrete Mathematics, so it's all going to be about discrete mathematics, and it's a really good building block for any other maths things. Discrete mathematics is so important as like just a normal understanding of maths. So let's just get straight into this. So what is a set? Well, let's start by introducing some important definitions. Our first definition here is that a set is a collection of well-defined objects. So we're using the word objects here because it's not just because math doesn't necessarily mean it's numbers. I mean, a lot of the time you will be dealing with numbers no matter what type of numbers they are, but sometimes you can have questions where it's not to do with numbers, it's to objects or people or whatever. So that's why a set is a collection of well-defined objects, and we have well-defined in commas, speech marks here because it's not always well-defined, but usually it is. It's really good to know what objects you're dealing with within a set. And our second definition here is that the objects inside the set are called elements or members of the set. So a set has elements inside it. That's what it essentially means. And we usually label our sets with capital letters, so like an A or B, but it can be neat as anything as long as you make it obvious what you set the label as. So you can have, if normally you'll see in questions or proofs that it says like let A be a set, so A is the set. And now we'll go over some very important sets that you might already know. So some important sets. So our first one here is the set that everyone starts on. It's the counting numbers, or as mathematicians know it, the set of natural numbers. So this is denoted by sort of a strange looking N. It's got another line in it, but that's just, and you can see all the letters for our sets do, but that's just the way you denote them. So the set of natural numbers is your numbers 1, 2, 3, 4, your counting numbers. So from 1 to infinity, just your basic counting numbers. And then our next set here is the set of integer numbers denoted by this Z, and this is your 0, plus or minus 1, plus or minus 2, plus or minus, so like negative 7's in the set, 10's in the set. It doesn't matter as long as it's a whole number. It doesn't matter if it's plus or minus, that is in the set of integers. However, there is a set between the set of natural numbers and the set of integers called the set of natural numbers and 0, which is a mixture. Sometimes it's also called just a set of positive integer numbers, where it's 0, 1, 2, 3. So it's 0 plus your counting numbers, but I'm sure you can come across that. It doesn't need its own little definition here. So, and then our next set here is the set of rational numbers. And I've done an example set on the screen here where it's 0, 1, 2 of 5, 0.756, ... So this is just a set of anything that can be written in the form of A over B, where A and B are integers and B isn't 0. So this essentially means that as long as it can be written as a fraction, then it belongs to the set of rational numbers. So it doesn't matter what numbers you use. You could have 254 over 573, for example, but that because it's written as a fraction, it is in the rational numbers. And even though I've written a decimal here, this decimal it's not infinite. So it can be written as a fraction. I don't know what the fraction is of it because I've just written it down, but it can be written as a fraction. That's why it's in the set of rational numbers. And now we move on to the set of real numbers, which is kind of like rational numbers, but essentially it doesn't matter if you have never-ending decimal points. It doesn't have to be written as a fraction. The definition of it really is that it's a set of all points on a number line, but this also can be equivalent to any number having a decimal expansion. It doesn't matter if it's infinite or not. So like pi and e, for example, they have never-ending decimal point places. So they are in the set, but they're not rational numbers because of their never-ending decimal places. And our final set here is the set of complex numbers, which I won't go too in-depth with because complex numbers are a bit more advanced than the first video to a new series. But essentially, there's real and imaginary planes, and they exist on there. This is another way to see it. So each set I went through is a part of it. So all the natural numbers, natural numbers or counting numbers are a part of the integers, and the integers are part of rational numbers, and it's so on and so forth. So these are just two pictures that I thought were very interesting and informative. Right, so let's move on to some set notation. If we want to say that a different value, x for example, is a part of a set, then we use this new symbol here, which looks like a little bit like a euro, weird E maybe symbol, and essentially all it means is an element of. So if you put x, this symbol, and A, it just means X is the element of A. So you can do this, like you might use it for questions, or you might see it in questions, and it's just a way to write it rather than saying writing out is an element of. There's some other notation you might need to know, whereas if a set has no elements, then it's called an empty set, and it is written with this sort of phi theta looking symbol, and that just means it's an empty set. And then if you're listing elements of a set, then you use the brackets with these squiggly brackets. Obviously you can't always list, sometimes you can just use the dot 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 if it goes off to infinity or whatever, but if you can list it, then you use brackets like this. So let's move on to when you can't list a set. What you'll do here, let's say there's too many elements, you'll use a defining property p of x. And so the way to see this more precisely is that if a is a set and px stands for some statement of x, then we write squiggly bracket x in a such that the two little the colon there means such that p of x is true. So the set of all elements x in a such that p of x is true. And I'm going to go into some examples now, so I'm going to switch over to the sketchbook and I'll show you some examples of this. So let's go into some examples of this defining property. So if I write this, n plus 3 colon n. First off, what does this mean? Well, this means that n plus 3 such that n is in the natural numbers, is an element of the natural numbers. So to find the actual set, to list it, what we have to do is to find some values in which some values n plus 3 such that n is the natural numbers. So what are the natural numbers? Well, these are just 1, 2, 3, dot dot dot. So this means n has to be one of these. And obviously you start with the smallest and go up. So n has to be that. So let's start with 1, n plus 3, 1 plus 3 equals 4. Next one, 2 is in the natural numbers. 2 plus 3 is 5. 3 is in the natural numbers. 3 plus 3 is 6. And this gives us our set. Now let's move on to a different question. So we have a different one here. Looks a bit similar, but it is different. So this is the next set, which says that n such that n plus 3 is in the natural numbers. So it doesn't mean that n has to be, but n plus 3 has to be. So n plus 3 must equal this one up here, 1, 2, 3. So if we take this first one here, so let's say 1, n plus 3 must equal 1, well, we could just do some linear little equation here to find that if we take 3 from both sides, n equals minus 2. And this gives us our first value here, minus 2. And if we do this for all of them, so 2 minus 3 equals minus 1, 0, 1. And as you can see, that n, such that n plus 3 is in natural numbers, still holds. So minus 2 is fine, such that minus 2 plus 3, which is 1, is it in the natural numbers? Yes, so this is true, so it still holds. So I hope this video on introduction to sets and set notation and different types of sets has been useful. Make sure to like, comment and subscribe, and I'll see you in the next video on our discrete mathematics series.